This is Chapter 7, Notes Part 2. And so in Section 7.6 in our McGraw-Hill text, they discuss the risks of nuclear power, using nuclear reactions to produce energy, and that energy being similar to what is the energy that is obtained from burning coal, and that is heat energy. And so we talked previously about how a nuclear power plant is similar to a coal burning power generation plant in the fact that the chief objective is to boil water and produce steam. And so both types of power plants have these huge boilers that contain water, and that water is heated to very, very hot temperatures, producing steam. And then that heat and that steam, which is water vapor or gas, therefore is going to be converted from this heat energy to electrical energy. The difference between the two types of plants is how the steam is generated, how the water is heated. And with a coal burning power plant, it's heated by combusting coal. In a nuclear power plant, it's done by nuclear fission reactions that produces the energy, the heat energy that boils the water. And the advantage of the nuclear power plant over coal burning is being more environmentally friendly from the standpoint that you're not releasing dangerous air pollutants into the air like you do when you're burning coal. Air pollutants like sulfur, nitrogen oxides, all of which are air pollutants and that contribute to the formation of acid rain. But the risk and downsides for generating electricity via nuclear reactions is that the waste that is generated, the nuclear waste, the spent nuclear fuel, the quandary over what to do with it. Right now, we just store it. And the problem with the waste is that it has what is called long half-lives. The isotopes that end up being formed from the breakdown, the radioactive decay of the uranium that's used in most nuclear power plants, that uranium gets radioactively decayed down into other elements. And these other elements are also radioactive. And they have long half-lives. So these elements, these isotopes that result, they will emit radiation for a long period of time because they have long half-lives. A half-life is the amount of time that it takes for half of the original amount of the starting material to decompose. And so if an isotope has a half-life of 1,000 years, that means that it'll take 1,000 years for half of the starting amount of that radioactive isotope to disappear. And so most nuclear power plants have these huge storage tanks where they store the nuclear waste on site. Other countries are trying to develop long-term types of underground storage options. And we here in the United States even contemplated that concept. In Nevada, at the location known as Yucca Mountain. But because of the environmental concerns over burying radioactive nuclear waste, What is that going to do to the soil, the different runoff? Is it going to contaminate groundwater systems? So on and so forth. Even though no one lives anywhere near Yucca Mountain, it's a isolated, desolate place. But still, is there a risk for groundwater systems and so on and so forth? So as of now, we have not used this Yucca Mountain site in Nevada to bury any nuclear waste. It's still being stored in huge storage containers on site at each nuclear power plant. Another risk of nuclear power plants is accidents. And there have been quite a few nuclear power plant accidents over the past 50 to 70 years of their existence. In 1986, the Chernobyl disaster in Kiev, Ukraine, it was one of the worst nuclear accidents in history. And so the nuclear power plant there and the nuclear reactor, the control rods help control the rate of the nuclear reaction. And it's very important what type of material that the control rods are made of, because you want them to be the least amount of reactive or flammable as possible. The control rods in the Chernobyl nuclear reactor that exploded in 1986, those control rods were made of graphite, which is carbon. In the United States, we don't use carbon-based control rods. We use boron-based control rods. So the control rods caught on fire at the Chernobyl plant. Why did they catch on fire? Well, they were doing some maintenance on that reactor number 4. And the technicians that were doing the maintenance, they allowed a power surge to happen. And therefore, it basically blew the whole system, that power surge. And so therefore, that power surge caused a nuclear explosion, and it ripped open the reactor. And there, because the reactor was ripped open, so here's your containment structure that holds the nuclear reactor. And this whole containment structure was blown open. And so not only did the reactor itself blow open and spill out nuclear material, but the steam generator was also blown open, and that hot steam at those extreme hot temperatures, that also caused an explosion. So you had this super hot water vapor under pressure, and then the containment structure ripping open, therefore causing a sudden release of all of that energy in that hot steam. And therefore, you also had a steam explosion. And so the reactions that took place when that Chernobyl reactor exploded, you had liquid water as a coolant running through the reactor. So that liquid water reacted with the carbon, the graphite that the control rods were made of, and that produced hydrogen gas, which is very explosive, as well as carbon dioxide gas. And then the hydrogen gas reacted with the oxygen in the air and produced more super hot water vapor, steam. And therefore you had another explosive element, that's steam. And so that containment structure was made of concrete. It blew open, and the steam generator blew open, the reactor itself blew open. And so 50 different radioactive isotopes that were in that nuclear reactor was released into the atmosphere. And those radioactive isotopes have very, very long half-lives. They range anywhere between 2 hours to 24,000 years. So some of the nuclear material had shorter half-lives, others had very long half-lives. And so one of those isotopes that were released that are radioactive is iodine 131. And it causes thyroid cancer. So after the Chernobyl disaster, uh, a lot of the people that were living near that plant developed thyroid cancer years after that explosion. And so iodine 131 is radioactive. It undergoes uh, radioactive decay to form a xenon isotope. It releases an electron, so that's beta emission. And it also releases a gamma particle. So it's also gamma emission. So a very dangerous isotope because of the radioactive particles that it breaks down and produces. And that's what causes the cancer. And so the consequences of that disaster, which was an accident that could have been prevented, it wasn't like the Fukushima plant in Japan in as a result of an earthquake causing a tsunami, and therefore a natural disaster causing the uh, the failure of the nuclear reactors. This was a man-made accident, and so people had to leave the Ukraine to never return. No one can or ever will live anywhere near where that Chernobyl nuclear plant was. Many injuries, many deaths, uh, a radioactive cloud. It covered a large part of not just Ukraine was affected, but other European countries as well. And so, therefore, at least 20 nations were affected. At least people in 20 nations had health effects, threatening effects as a result of the release of all that radioactive material. And so, future cancers that resulted range anywhere between 7,500 to a million that were speculated to be caused by the radioactive material that people were exposed to up to 2 kilometers, 2,000 kilometers away from the actual site. And so it's very dangerous. All that radioactivity got into the environment, into our atmosphere, into the soil, therefore into the food chain. And I'm sure it caused a lot of uncertainty and fear in the populations of people that lived within a 2,000 or so mile radius of Chernobyl. Political consequences, of course. Um, there was a big cover up by the Soviet Union about the accident and why it happened. Um, Sweden and Poland were the main nations to bring lots of attention to the incident because their countries were affected. The radioactive material just didn't stay stagnant over the Ukraine and Russia, but it spread over Europe over a 2,000 mile radius. And so um, that accident caused many, many nations to be wary about ramping up or even starting a nuclear power program in their country. So there are lots of ramifications for this man-made disaster, which, like I stated earlier, very much unlike Fukushima, which a natural disaster caused the meltdown of three of their reactors. And those flood waters is what was the culprit because it knocked out the electrical generators needed for cooling water. And so without the cooling water, the nuclear reactor overheated, and therefore the nuclear fuel overheated, and that started a fast, uncontrollable uh, chemical chain reaction that generated hydrogen gas at fast rates, much faster than normal if the cooling water would have been available to control the rate of the nuclear reactions. And so hydrogen gas was being generated too fast. And as I stated earlier, hydrogen gas is very explosive. And so therefore, uh, one of the actions that they took is to vent the hydrogen gas. And in trying to vent out the hydrogen from the nuclear um, reactor, what that also did was not only release that hydrogen gas so it wouldn't build up and cause an explosion like what happened in Chernobyl, but also what escaped in addition to the hydrogen gas were radioactive uh, isotopes like iodine-131. And so despite them trying to vent a lot of that hydrogen gas, explosive reactions still took place in spite of their attempts to vent the hydrogen gas. And so, again, dangerous radioactive isotopes, which included the iodine-131, were still released into Japan. And so hydrogen gas being very explosive was a big part of the disaster at Chernobyl as well as Fukushima. And hydrogen gas reacts with oxygen gas in a combustion reaction. And it produces water vapor or steam. And so in this reaction, we can draw the Lewis structures of each of these reactants. We learned how to draw Lewis structures in an earlier chapter. So I'm rewriting the reaction, only this time I'm drawing the Lewis structures. And this is the Lewis structure of water, H2O. So we also learned about bond energy in an earlier chapter, units of kilojoules per mole. And so each of these types of bonds, there are 3 types involved in this reaction: a hydrogen-hydrogen single bond, an oxygen-oxygen double bond, and you got an oxygen-hydrogen single bond. And every water molecule has 2 oxygen-hydrogen single bonds. And so the bond energies for each of these 3 types of bonds are shown in this table. So for my hydrogen molecule, there's only 1 hydrogen-hydrogen single bond per H2 molecule. But there are 2 moles in this of hydrogen molecules in this reaction, and therefore 2 moles of bonds. And so the hydrogen-hydrogen single bond gets broken in this reaction. For reactants, their bonds are broken, and the atoms then get free to rearrange to form products. And therefore the oxygen-oxygen double bond is also broken. And in our balanced reaction, our stoichiometry, or the numbers that are in front of each reactant, that tells us how many moles of that reactant or that product are involved in the reaction. So if there's not a number in front of a reactant or a product, then it's understood to be 1. So we only have 1 mole of O2 in the reaction, and therefore 1 mole of bonds. And there's only 1 bond, 1 OO double bond in the O2 molecule. And so for H2, the energy per bond is 436. For O2, the energy in that OO double bond is 498. Our product is formed by forming bonds. And so water is our product, and we have two bonds in one water molecule, two OH single bonds. And there are 2 moles of water in the reaction. And therefore we have 2 moles of bonds. Correction, that's 4 moles of bonds. Because again, we've got 2 molecules of water, and in each molecule there are 2 OH single bonds. So that's going to be a total of 2 times 2, which is 4 moles of bonds. And each OH single bond has a bond energy of 467. So therefore, to calculate the total energy, so 436 kilojoules per mole, and there are 2 moles. The moles cancel out. So 436 times 2 is 872 kilojoules. And then for the O2, the bond energy is 498 kilojoules per mole. And there's just 1 mole of it. So 498 kilojoules. And then finally for the water, bonds are being formed. And 467 kilojoules per mole times 4 moles. And that is 1868. And so the question asks, how much energy was released per mole of hydrogen and per gram of hydrogen? And so what we need to do to answer that question is to calculate the total energy difference. It's going to be equal to the energy of the reactants plus the energy of the product. And in this case, in this reaction, we only have one product, and that's water. But we have two reactants, the hydrogen and the oxygen. And so when bonds are broken in reactants, that is an endothermic process. However, when bonds are formed to make products, that is an exothermic process. Endothermic processes, energy is absorbed. So therefore, the energy has a positive sign. However, exothermic processes, energy is released. And that is a negative sign. So therefore, our total energy difference is therefore going to be the energy of our reactants, and we've got two of them, H2 and O2. These are the energies of our reactants, 872 plus 498. Units are kilojoules, plus the energy of our product. We only have one product, and that's water. And that is 1868. But water is a product and bonds were formed, and that's an exothermic process. So I need to put a negative sign next to my energy for my product. So I do my math. 872 plus 498. And then to that add a negative 1868. Your energy difference comes out to be a negative 498 kilojoules. So the combustion of hydrogen gas is an exothermic process. And that's because our total energy difference is negative. Because our total energy difference is negative, that means that the reaction overall is exothermic. If our total energy difference would have been positive, then our reaction would have been overall endothermic. Question 2, we talked about iodine-131, radioactive isotope that was released from the nuclear fuel in the Chernobyl and the Fukushima nuclear disasters. And so iodine, if I say iodine, I could be talking about the atom, which is neutral. No charge. Or I could be talking about the molecule, which is two iodine atoms bonded together. also neutral, no charge. Or I could be talking about the iodide ion, I minus. It has a -1 charge. And so the iodide atom, iodide is in group 7A on the periodic table. So it has 7 valence electrons. The iodine molecule, I2, has 14 valence electrons. Each iodine has 7. So to draw its Lewis structure, I put my single bond connecting the 2 iodine atoms together. That's 2 electrons. Then I'm going to put 6 electrons around each iodine in the Lewis structure, showing all 14 valence electrons. And then the iodide ion, I minus, has 8 valence electrons. 7, because iodine is in group 7. The -1 charge means that the iodine atom turned itself into the iodide ion by gaining 1 electron. And so the iodide ion has a full octet of 8 electrons around it. And the way we draw Lewis structures for ions, we put a bracket around them and put the charge outside of the brackets. The one that's more reactive is the iodine ion. Why is it more reactive? Because it is charged. The iodide 131 that's implicated in thyroid cancer, that's the atom. And it comes from nuclear decay reactions that started with uranium-238, I do believe. I do believe both of those nuclear power plants at Chernobyl and Fukushima, their reactive material, the fuel, so to speak, for their reactors was uranium-238. And then uranium-238 goes through a series of chain reactions of radioactive decay to form other radioactive elements that are smaller in atomic mass. And iodine-131 is one of those. So at Chernobyl, hydrogen gas was produced by the reaction of water, that hot steam, with that hot graphite that the control rods were made of. At Fukushima, the hydrogen gas was produced by the reaction of the water with the zirconium that's found in the alloy that composed the outer casing of the fuel rods. So the hydrogen gas that was produced as a result of both accidents was produced 2 different ways. And so the first part of the question wants us to write a balanced reaction for hydrogen gas formation at the Fukushima plant, in which zirconium is going to react with the hot steam, which is water vapor or water in a gas form. So the zirconium, solid metal, reacting with the water vapor, and that reaction produced hydrogen gas. and zirconium oxide. So we knew we already had the H2, and then we also have to balance the reaction on both sides. So there need to be a zirconium and an oxygen on the right as well. So those were the two products of the reaction. And they didn't use any other material that would have been reactive. Zirconium is very stable. It's not very reactive like the graphite that was used in the control rods at the Chernobyl plant. Zirconium is used in the fuel rods that hold the uranium material because zirconium is not very reactive. It's very stable under normal conditions. So when the nuclear power plant is running the way it's supposed to run, there's not an earthquake and tsunami that floods the place and knocks out your generator and therefore knocks out your cooling water supply, causing the reactor to overheat. And overheating at the high temperatures that that reactor got at Fukushima, that's what caused the zirconium to react with the steam. But because it was the reactor was out of control. But when you're controlling the reactor with the cooling water, the zirconium is not going to react with the steam because the steam won't get hot enough for it to react with the zirconium. It's that cooling water that prevents that. And because the tsunami knocked out the generator that controlled the cooling water, then the reactor got too hot and therefore it exploded, causing the zirconium to react with the steam. And so, because it's very stable and unreactive, it does not react with the uranium itself. And it's the neutrons that start the radioactive decay of the uranium. So only the uranium will react with the neutrons that are bombarded into the nuclear reactor. The graphite material does not react with the neutrons. So that's the good thing about the zirconium. Well, what's the bad thing about the zirconium? So even though zirconium does not react with neutrons, it is heat sensitive. And so when the cooling water got knocked out by the tsunami, then the reactor overheated, and the zirconium being very heat sensitive, it reacted with the hot steam. And so that cooling water failure caused the zirconium to get melted by the steam. And therefore, once the zirconium covers the fuel rods, so those are the uranium pellets inside the fuel rod. And so when the cooling water failed at the Fukushima plant, then the hot steam reacted with the zirconium and melted it away. From those uranium pellets, and that exposed that radioactive uranium material and therefore allowed it to escape. And so that's the end of the first video for Chapter 7, Part 2